Welcome to this problem-solving session. Today, we'll tackle an interesting challenge, problem number 2131, longest palindrome by concatenating two-letter words. In this problem, we'll explore approaches to find the longest palindrome that can be formed by concatenating two-letter words. Let's dive in. In this problem, you are given an array of strings called words, where each string consists of exactly two lowercase English letters. The goal is to create the longest possible palindrome by concatenating these strings. A palindrome is a sequence that reads the same forward and backward. Now, there are some constraints to keep in mind. Each string in the array can be used at most once, and you are allowed to rearrange or reorder the strings as needed to form the palindrome. The output should be the length of the longest palindrome you can construct. If it's not possible to form any palindrome, the function should return 0. To understand this better, let's look at the first example. Here, the input array is LC, CL, GG. The output is 6. Here's why: we can take LC and CL, which are reverse pairs, and use them to form the palindrome LCCL. Additionally, the string GG can be placed in the middle, since it's already a palindrome by itself. This forms the full palindrome LCGGCL, which has a total length of 6. Moving to the second example, the input array is AB, TI, YT, LC, CL, AB. The output here is 8. In this case, TI and YT can be paired to form TYYT, and LC and CL can be paired to form LCCL. Since the string AB appears twice, both copies can be used to form ABAB. Combining these, we get the palindrome LCLABABTIAT, which has a total length of 8. Continuing with the third example, the input is CC, LL, XX, and the output is 2. Here, none of the strings have reverse pairs, but we can use one of the CC strings to form the palindrome CC. This gives us a total length of 2. Now, let's consider the constraints. The number of strings in the input array can be as large as 100,000, so our solution needs to be efficient. Additionally, each string is guaranteed to have exactly 2 characters, and all characters are lowercase English letters. Finally, let's examine some edge cases. If there is only one pair of reverse strings, such as AB and BA, then the longest palindrome we can form will have a length of 4. On the other hand, if no reverse pairs exist, the only possible palindrome might come from a word like AA, which is already a palindrome, and its length would be 2. If all the words in the array are identical, such as AA, the length of the palindrome will depend on how many pairs we can form, with one unpaired word possibly placed in the middle. These notes will help clarify how to handle special cases efficiently and ensure we cover all possibilities when solving the problem. When tackling this problem, one approach we might consider is the brute force method. This involves trying every possible permutation of the two-letter words in the input array, concatenating them in different orders, and checking if the resulting string forms a palindrome. To validate if a string is a palindrome, we compare the first half of the string with the reverse of the second half. While conceptually straightforward, this approach quickly becomes impractical. Since the input size can be as large as 100,000 words, the number of permutations grows factorially. This means the time complexity is O(n), which is computationally infeasible for large datasets. As a result, this method is not suitable for solving the problem efficiently. To address the inefficiency of the brute force approach, we can employ an optimized strategy that leverages a hash map and the symmetry inherent in palindromes. First, recall that a palindrome reads the same forwards and backwards. This symmetry creates natural pairings. For a word like AB, its reverse BA forms a complementary pair. Additionally, some words, like AA, are already palindromes and can play a unique role by potentially forming the center of the final palindrome. To maximize the palindrome's length, we need to pair words like AB with BA as much as possible, while carefully managing the AA words to ensure only one unpaired AA is used at the center. The algorithm begins by using a hash map to count the frequency of each word. For non-palindromic words, we find their reverse and add the minimum frequency of the 2 to the palindrome length, as each pair contributes 4 characters. For palindromic words like AA, we include their pairs and track if one unpaired word can be used at the center. Finally, we multiply the total pairs by 4 and add 2 if there's a leftover center word. This optimized approach is efficient because it uses a hash map to process the words in linear time, resulting in an O(n) time complexity, where n is the number of words in the input array. Compared to the brute force method, which is computationally prohibitive, this approach is specifically designed to handle large input sizes by avoiding unnecessary computations. While the brute force method is simpler to understand, it cannot scale effectively. The optimized strategy strikes the right balance between efficiency and correctness, taking full advantage of the problem's constraints and the properties of palindromes. This makes it the ideal choice for solving the problem within the given constraints, offering a solution that is both fast and scalable. In this problem, we are given an array of two-letter words, and the goal is to determine if we can concatenate some or all of the words to form a palindrome. Remember, a palindrome is a string that reads the same backward as it does forward. To solve this, we need to focus on two key properties of palindromes. First, the characters in the first half must mirror those in the second half. Second, for strings of odd length, at most one character can remain unpaired and sit in the center. For two-letter words, this simplifies our task. Words like ab and their reverse, ba, can pair up to contribute to a palindrome. Meanwhile, self-mirrored words, such as cc, can either pair with another identical word or occupy the center. To approach this problem efficiently, we use a hash map, or frequency map, to count the occurrences of each word in the array. To build the solution, we start by iterating through the array of words. For each word, we check if its reverse already exists in the frequency map. If it does, the two can pair to contribute to the palindrome, and we reduce the frequency of the reverse word in the map. Next, for self-mirrored words like cc, we track their count separately. These words are unique because they can either pair with other self-mirrored words or occupy the center of the palindrome. After processing all the words, we need to handle the center. At most, one self-mirrored word can remain unpaired to occupy this position. If there are multiple unpaired self-mirrored words, the extra ones cannot be used. Finally, if all pairs are valid and no more than one self-mirrored word is left unpaired, then forming a palindrome is possible. Now, let's highlight some key insights that make this algorithm work. First, the pairing of reversed words and the limited use of self-mirrored words ensures that the final string satisfies the properties of a palindrome. Second, using a frequency map is crucial for efficiency. It allows us to check and update word counts in constant time on average, making the solution scalable. Third, we handle edge cases effectively. For example, an empty array always results in a valid, though trivial, palindrome. Arrays with only self-mirrored words, like cc or aa, can form a palindrome as long as at most one remains unpaired. On the other hand, if there are no reversible pairs in the array, forming a palindrome becomes impossible. Regarding complexity, the algorithm runs in O(n) time, where n is the number of words in the array, since we process each word once. The space complexity is also O(n), given the hash map stores frequencies of unique words. Let's walk through an example to see the algorithm in action. Consider the input array ab, ba, cc, cc, aa. We start with an empty frequency map. First, we process ab and add it to the map, resulting in ab1. Next, we process ba, which is the reverse of ab. Since ab exists in the map, the two words pair, and we remove ab from the map, leaving it empty. Moving on, we process cc, a self-mirrored word, and add it to the map, resulting in cc1. The next cc pairs with the first, so we update the map to cc0. Finally, we process aa, another self-mirrored word, and add it to the map, resulting in aa1. At this point, all pairs are valid, and aa can occupy the center since it is the only unpaired self-mirrored word. Thus, forming a palindrome is possible in this case. This Python solution solves LeetCode problem number 2131, longest palindrome by concatenating two-letter words, by leveraging the collections counter class to efficiently count word occurrences. The code starts by creating a counter object, word_count, to store the frequency of each word in the input list. The variable palindrome_length is initialized to 0 to track the total length of the palindrome we will construct, and used _middle as a Boolean flag to manage the use of a central mirror word, like AA or BB, in the palindrome. The solution iterates over each word in the counter. Words are divided into two categories. 1. Mirror words. These are words like AA, BB, where both characters are identical. If the count of such words is even, all of them can be used to contribute to the palindrome. If the count is odd, one word must be left unused, but it can potentially serve as the middle word of the palindrome. 2. Non-mirror words. These are words like ab, cd, where the two characters are different. For such words, we check if their reversed counterpart, e.g., ba4ab, exists in the counter. The number of valid pairs is determined by the minimum frequency of the word and its reverse, and these pairs contribute to the palindrome length. After processing all words, the code checks if any mirror word has been reserved for the middle of the palindrome, indicated by the used _middle flag. If so, an additional 2 is added to the palindrome length. The function finally returns the calculated palindrome _length. This solution is efficient, running in O(n) time complexity, where n is the number of words, since each word is processed only once. The use of the counter class ensures that counting and lookup operations are fast, making this approach suitable for large inputs. Here, we start by importing the necessary packages and defining our solution class. The method longestPalindrome takes an array of two-letter words and calculates the length of the longest palindrome that can be formed by concatenating these words. We use a hash map called wordCount to store the frequency of each word in the input array and initialize two variables, palindrome length to keep track of the total length of the palindrome, and use middle to indicate whether we've utilized a mirror word, like AA or BB, as a middle piece. First, we iterate through the array of words, updating the count of each word in the hash map. Next, we loop through the entries in the hash map, checking if the current word is a mirror word, meaning both characters in the word are the same. If it is, we calculate its contribution to the palindrome length based on whether its count is even or odd. For odd counts, we leave one of the words aside as a potential middle piece, setting the used middle flag to true. Now, for non-mirror words like ab and ba, we calculate how many such pairs can be used. To do this, we reverse the current word and check if its reversed form exists in the hash map. If it does, we take the minimum count between the two words, multiply it by 4 to account for their contribution to the palindrome length, and then set their counts to 0 in the hash map to prevent double counting. After processing all the words, we check if we used a middle mirror word. If the used middle flag is true, we add 2 to the palindrome length to include that central piece. Finally, we return the total palindrome length, which represents the maximum length of the palindrome that can be formed with the given words. Here, we are working with the input array ab, ba, aa, bb, aa, and breaking down the solution step by step. First, we initialize the variables. The word_count dictionary tells us how many times each word appears. For example, ab and ba appear once each, while aa appears twice. The palindrome _length starts at 0, and we use used_middle to track whether we've used a single mirrored word as the center of the palindrome. Now, we look at the word ab, which is not a mirror because ab does not equal its reverse, ba. However, since ba exists in the word_count, we can form one pair. Each pair contributes 4 characters to the palindrome, so we add 4 to palindrome _length and mark both ab and ba as used by setting their counts to 0. Next, we process aa, which is a mirror because it equals its reverse. Since it occurs twice, we use all occurrences and add 4 characters to the palindrome length, bringing the total to 8 so far. Now, we process the word bb, which is another mirror word. Since it occurs only once, we can't form a pair, but we keep it aside to possibly use as the center of the palindrome by marking used_middle as true. At this point, we add the middle word. Since used_middle is true, we add 2 characters to the palindrome _length for the center, resulting in a final length of 10. This is the longest palindrome we can form for this input. In the second example, we are given the input, ba, cc. After initializing word_count, we see that ab and ba each appear twice, while cc appears once. The palindrome _length starts at 0, and used_middle is false. We first process ab, which is not a mirror. Since ba exists, we can pair all occurrences. There are 2 pairs, contributing 8 characters to the palindrome. We add this to the palindrome _length and mark both ab and ba as used by setting their counts to 0. Next, we process the word cc, which is a mirror. Since it occurs once, we don't add anything to the length for now but mark used_middle as true to use it as the potential center of the palindrome. After processing all words, we add the middle word. Since used underscore middle is true, we add 2 characters for the center, bringing the palindrome underscore length to 10. This gives us the final output of 10 for this example. Now, we move on to the third example, where the input is AA, BB, CC, DD, AA, CC. We start by initializing word underscore count, which shows AA and CC each appear twice, while BB and DD appear once. The palindrome underscore length is initially 0, and used underscore middle is false. First, we process AA, which is a mirror and appears twice. Since the count is even, we use all occurrences, adding 4 characters to the palindrome length. Next, we process the word BB, which is also a mirror but appears only once. Since the count is odd, we don't add anything for now, but we mark used underscore middle as true to potentially use BB as the center. Then, we process CC, which is a mirror and appears twice. Since the count is even, we use all occurrences, adding another 4 characters to the palindrome length, making it 8. Finally, we process DD, which is a mirror and appears once. Again, since the count is odd, we don't add anything to the length, but since used underscore middle is already true, we don't update it further. At the end, we add 2 characters for the center because used underscore middle is true, resulting in a final palindrome underscore length of 10 for this example. Here, we start by analyzing the time complexity of the solution. The first step involves counting the occurrences of each word in the input list using Python's counter. Since the counter function iterates through the entire list of size n, this step takes n time. After counting, the algorithm iterates over each unique word stored in the word underscore count dictionary. Let's denote the number of unique words as m. Iterating through these unique words takes m time. Next, for each word, we perform a series of constant time operations, checking if the word is a mirror, reversing the word, and processing reverse pairs if they exist. All of these operations are 1 for each word. Since we process each word only once, the total contribution to the time complexity from these operations is m. Additionally, the algorithm includes an optional step to add a middle mirror word to the palindrome, if applicable. This is also a constant time operation, requiring 1. Combining all the steps, the total time complexity is primarily determined by the counting of words, which is n, and the iteration over unique words, which is m. Since the number of unique words m is at most equal to the total number of words n, we can simplify the overall time complexity to n. This efficient reduction ensures that the algorithm is scalable even for larger inputs. Now, let's examine the space complexity. The primary contributor is the counter dictionary, which stores the frequency of each unique word. In the worst case, where all words are unique, the dictionary requires m space, where m is the number of unique words. As we've established, m is bounded by n, so this step takes n space. Additionally, the algorithm uses a constant number of variables, such as palindrome underscore length and used underscore middle, which require 1 space. Temporary space is also used when reversing words, but since each word is of fixed length 2, this requires only 1 space. Finally, the input list itself occupies n space, as it directly depends on the number of words in the input. Combining all the factors, the overall space complexity is dominated by the storage required for the counter dictionary, which is n. Thus, the total space complexity of the solution is n. To put this into perspective, consider a brute force approach that generates all possible concatenations of words and checks if each forms a palindrome. This would involve n squared pairs of words and a palindrome check for each concatenation. Since checking if a string of length k is a palindrome takes k, and k could be as large as 2n in the worst case, this results in a total complexity of n cubed. In contrast, the provided solution optimizes the process by using frequency counting and direct pair matching, reducing the complexity from n cubed to n. This makes it significantly more efficient and practical for large inputs. Finally, let's break down the best, average, and worst-case scenarios for the algorithm. In the best case, where all words are identical, the algorithm still processes each word exactly once, resulting in n time complexity. In the average case, with a mix of unique and duplicate words, it processes each unique word and its reverse, which still leads to n time complexity. In the worst case, where all words are unique, each word and its reverse are processed once, again resulting in O(n) time complexity. Mathematically, the overall time complexity is dominated by the counting of words, O(n), and the iteration over unique words, O(m). Since m is at most n, the total time complexity remains O(n). Similarly, the space complexity is dominated by the storage needed for the counter dictionary, which is O(n). With only constant space used for variables and temporary strings, the total space complexity also remains O(n). When working on problems like this, there are a few common mistakes to avoid. First, assuming that all strings in the array can form a palindrome without proper validation can lead to incorrect results. Remember, not every collection of strings will align to create a valid palindrome. Symmetry is key. Most characters need to have even frequencies, with at most one character allowed to appear an odd number of times in the case of odd-length palindromes. To fix this, always validate character frequencies and symmetry before attempting to construct permutations. Another common pitfall is relying on permutations to find solutions for large input sizes. Permutations grow factorially, making them computationally expensive and impractical as the input size increases. Instead, opt for frequency-based or hashing approaches, which work in linear or near-linear time. Finally, edge cases like empty strings or single-character strings can often cause errors, such as division by zero or faulty assumptions about the problem's constraints. Always handle these edge cases explicitly at the start of your code to avoid unexpected runtime issues. Another mistake to watch out for is overlooking two-letter substrings that complement each other. For example, pairs like AB and BA can form part of a palindrome when combined, but it's easy to miss these relationships. To address this, you can use a hash map or a similar data structure to track reverse substrings efficiently, allowing you to identify complementary pairs quickly. Another issue arises when developers mix up time complexities of different approaches. For instance, it's easy to assume an approach is optimized without carefully analyzing its computational cost. This can lead to choosing an O(n) squared solution when an O(n) log n alternative would be more efficient. To avoid this, always compute and compare the time complexities of your methods so you can make an informed decision about which approach to use. Now, let's focus on insights that are particularly relevant for interviews. A key concept to remember is that palindromes require symmetry. For strings, this means all characters must appear an even number of times, except for one character in the case of odd-length palindromes. Understanding this symmetry can guide your approach to solving related problems. Hash maps are another powerful tool in palindrome-related challenges, as they allow you to efficiently track character frequencies or reverse substrings for quick lookups. Additionally, don't forget to account for edge cases, such as empty strings, single-character strings, or arrays with duplicates. These scenarios often come up in interviews to test your thoroughness. If permutations seem computationally infeasible due to their factorial complexity, consider switching to greedy or frequency-based approaches to simplify the problem. For further practice, you might explore related problems like LeetCode 266, which deals with palindrome permutations, or LeetCode 5, which focuses on finding the longest palindromic substring. Finally, let's look at some alternative approaches you can use. The frequency count approach is a great option when you want to avoid the inefficiency of generating permutations. By counting characters and validating frequencies, you can solve these problems in O(n) time, though it does require additional space for hash maps. Another useful method is the two-pointer technique, which is effective for checking or constructing palindromes directly in place. However, this technique may not be ideal for tasks that involve permutations or more complex validations. For problems like finding the longest palindromic substring, dynamic programming can be a powerful tool. It allows you to break the problem into smaller subproblems, but the trade-off is higher time and space complexity, typically O(n) squared. Choosing the right approach depends on the specific problem constraints and the trade-offs you're willing to make. Great work on completing the problem. Today, we explored how to solve longest palindrome by concatenating two-letter words and covered key takeaways, including hash map usage and pattern recognition for palindromes. Don't stop here, keep practicing and applying these concepts to similar problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!